What up, y'all? It's Dr. Kim Thug, and today we're talking about the most important chemical to modern humanity. You won't find any of this chemical in your house, no, but like 95% of the things in your house require this chemical to come into existence, and I'm actually not really exaggerating here. Medicines, the raw materials to make all kinds of polymers and such, metal refining, dyes, agricultural needs. It was said as early as like the 1800s that the ability of a country to make this chemical is a good measure of their industrial capability overall. And that's still true today. So what is this wonder chemical? And how do we get to using it for like everything? And is it really actually the most important chemical? Yes. Yes, it is. And today we're talking about oil of vitriol, better known as sulfuric acid. Sulfuric acid is a mineral acid made of sulfur, oxygen, and hydrogen, and it is one of the strongest acids in existence. And yeah, if you're wondering that oil of vitriol, that's connected to the word vitriol that it is. And we're going to talk about that. In order to do that, we got to start with the ancients. The ancients described these substances called vitriols, which are these colorful, glassy minerals that occur mostly underground. They classified them by their color because there were several of various colors, but blue and green were probably the most famous. Now, these minerals are very water soluble, and for this reason, the ancients were able to find a whole lot of uses for them, a few that still survive to today. Blue vitriol, for example, is copper sulfate pentahydrate, and this still finds use as a fungicide and for controlling algae growth. It also has like a couple random niche like veterinary uses, and I guess if you've ever worked on a vineyard, you might know it as part of this stuff called Bordeaux mixture. But like it used to get used in cosmetics and pigments because it's a very pretty blue color, but we don't do that as much anymore because we know copper salts aren't good for you like that. Green vitriol does still have some medical uses because green vitriol is iron sulfate heptahydrate and gets used as an iron supplement for people with anemia. It also historically got used in fabric dyeing, as well as mushroom identifying and gold refining, but its most important use historically was in making ink, specifically iron gall ink, which was this like super important ink for 1400 years. But these vitriols themselves were kind of some of the earliest commodity chemicals. They weren't like an industry by our current day standards, but there were like projects dotted throughout the ancient world to manufacture these vitriols intentionally. But ultimately what this meant was that these vitriols were around and people had been playing with them for several hundreds of years. And that is when and how we ended up striking oil. By which I mean oil of vitriol. So you see, as with so many good things in history, somebody at some point took these vitriols and put them in a distillation apparatus and heated them up and collected the vapors that came off. And yes, you can distill rocks. In the case of green vitriol, when you heat it up, it releases the water that's trapped in the crystal. And then once all the water is gone and you keep heating it, the actual iron sulfate itself decomposes into rust, iron oxide, and a mixture of these two gases. Sulfur dioxide, which is a sulfur atom attached to two oxygens, and sulfur trioxide, which is a sulfur atom attached to three oxygens. Now, those two gases, those are the key ingredients, or at least the sulfur trioxide, because the sulfur trioxide, that, if it reacts with water, like say the water that came off in the beginning, it turns into sulfuric acid. It is generally believed that this dry distillation of these vitriols is what got us the oil of vitriol in the first place, hence the name. Another method that was known by the 1600s, although perhaps not the first way it was done, was by burning brimstone with saltpeter or sulfur and potassium nitrate. Because when you take sulfur and you burn it, it turns into sulfur dioxide and sulfur trioxide. Same thing that happens when you heat the green vitriol. But if you have some potassium nitrate around, that potassium nitrate will react with the sulfur dioxide and turn it into sulfur trioxide. And now all of it is sulfur trioxide, and that mixes with water and you get your sulfuric acid. Not sure if that's how it got done first, but by the 1600s, people were starting to understand that this oil of vitriol, this highly reactive, highly corrosive liquid, was maybe about something. So yes, that is where the modern definition of vitriol comes from. Oil of vitriol is the most powerful naturally occurring acid, and it is pretty famous for how destructive and dangerous it can be, particularly if it's hot or concentrated. When it is hot or concentrated, it reacts with virtually everything, except like glass and gold and lead. but most metals will just like corrode or dissolve into it, and organic materials are just like obliterated. Cloth, flesh, wood, paper, all of that just doesn't stand a chance. But see, there's a flip side to it being so strong. Because sulfuric acid is so strong, you can make the other important strong acids using sulfuric acid. If you take sulfuric acid and you mix it with sodium chloride, the sulfuric acid exchanges its proton for the sodium in the sodium chloride, and you get hydrochloric acid and sodium sulfate. Same thing happens if you take sulfuric acid and you mix it with potassium nitrate. It exchanges its proton for that potassium, and you get potassium sulfate and nitric acid. This is actually one of the early documented uses for oil of vitriol, to take sodium chloride and potassium nitrate, mix them into the oil, and get a mixture of hydrochloric acid and nitric acid. That famous acid mixture aqua regia used for dissolving gold. As time went on, there was just a growing demand and a growing need for this very dangerous but very handy chemical. Up until this point, the two ways of making sulfuric acid were still either distilling these vitriols or burning sulfur. And then 1746 rolled around, and a lovely gentleman by the name of John Roebuck developed the first large-scale industrial process for making this stuff, called the lead chamber process. John Roebuck's lead chamber process really innovated the chamber in which the process took place. Previously, the chambers were made of glass, and thus this limited the size that they could be made. But these lead-lined chambers could be made large enough to make 100 pounds of acid or more at a time, and make it at a higher concentration than previously available. This ultimately meant that sulfuric acid was now like a tenth of the price and able to seep into all kinds of other industries, because at this point we already knew that it was kind of handy for doing a whole bunch of things. One of those early kind of minor but to me fun uses was in textiles, where sulfuric acid replaced sour milk as the bleaching agent for cloth. That was actually like a relatively minor use compared to what the actual first major industrial use of sulfuric acid was. The first major industrial use for sulfuric acid was in making sodium carbonate. Like washing soda, like base, which to me, I'm just like, all right, so we use the strongest acid in the world to make base, bet. But sodium carbonate's a really important chemical, like very, very important historically, soap making, glass making, cleaning things, cooking uses, probably one of the top 5 most important commodity chemicals at the time. And sulfuric acid in the LeBlanc process was kind of the way to make it at the time, where you take sulfuric acid and you mix it with sodium chloride. Remember, as I told you, you make sodium sulfate and hydrochloric acid gas. But in this case, what you wanted was the sodium sulfate, because then that 2 more steps, you turn that into sodium carbonate. Fun fact about these alkali works, as they were called, these plants that were set up to start making sodium carbonate using this process, they were so prolific in their production of sodium carbonate in this process, and so careless about what they did with the hydrochloric acid gas that is produced in the process, that they led to the first environmental regulation ever put in place in the UK. It was called the First Alkali Act of 1863. Because up until that point, these alkali works were just like pumping this hydrochloric acid gas out into the air, like around these facilities that were not like sequestered. No, you had just like hydrochloric acid gas just like seeping out into the forest. What a time to be alive, yo. Oh my God. But yeah, first major industrial use of sulfuric acid, making sodium carbonate. And that kind of just skyrocketed the demand for sulfuric acid, because the demand for sodium carbonate was already crazy. And this alone was enough to make people start trying to figure out better ways to make sulfuric acid. But before we figured out a better way to make it, we actually figured out what continues to today to be our biggest use for it: phosphate-based fertilizers. So let me tell you a story. Up until about the 1840s, the only real meaningful source of phosphate fertilizer for crops was like guano or bones, maybe compost and things like that. But the demands of agriculture at the time were so great that graveyards were getting robbed for the bones to make fertilizer to try and meet the demands of the growing population around the 1830s, 1840s. And then everything changed when this agricultural scientist, John Bennett Laws, in 1842 patented this stuff he called superphosphate, which I I kind of like that name. I ain't gonna front. I just think it's a funny name, superphosphate. But it was super important actually, because what he figured out is that if you take sulfuric acid and you combine it with phosphate-rich minerals or coprolites, which were fossilized dinosaur poop, it reacts with everything in there, of course, but specifically the phosphates in there, and makes these soluble phosphate salts. And that kind of revolutionized our agricultural industry overall. This was the birth of the modern fertilizer industry, as well as what allowed for our modern industrial agriculture practices to flourish. And today, this is still the major use for sulfuric acid, making these superphosphate salts, and also just making phosphoric acid, because that also has like a bunch of very handy uses. But now I got to talk about dyes for a second. So if you didn't know, prior to like the 1850s, if you wanted to say a pretty purple piece of cloth something, it was going to cost you your firstborn child, because most dyes came from plants and purple was particularly difficult to source and produce. But that all changed with the accidental synthesis of mauve, an inexpensive, fully synthetic purple dye that worked really well for cloth. It was so popular that it in and of itself gave birth to the synthetic dye industry, because now we were like, well, we can do this, huh? Now that, shockingly, didn't involve sulfuric acid. However, about 10 years later, in 1868, sulfuric acid was used to synthesize rose madder, which was a very popular red dye previously only obtainable from plants. This dye, rose madder, is a molecule called alizarin, and we knew what that molecule looked like. We knew its structure. We also knew the structure of the thing that we got made from, which meant that this dye, made with sulfuric acid and a few other things, was one of the first examples of my job, of synthetic organic chemistry as a profession. Thank you, sulfuric acid. Appreciate it. But there's more. Because of how successful these synthetic dyes were and this new burgeoning art of synthetic chemistry seemed to be, the company Bayer was founded, one of the earliest pharmaceutical companies to ever exist. And in 1890, sulfuric acid was once again used to synthesize one of the most successful and widely used drugs in the history of humanity, aspirin. And a lot of places still make it this way, using sulfuric acid to catalyze a reaction between salicylic acid and acetic anhydride. So I think it's worth mentioning that prior to this point, we didn't really understand sulfuric acid as a chemical. We knew that it was an acid, but it wasn't until like the late 1800s, early 1900s that we were really starting to define what an acid is as a chemical, and like the strengths of different acids and the types of different acids. And sulfuric acid did a whole lot to help us figure that out, given that it was, in fact, the strongest acid. And now feels like a pretty good time to actually talk about what makes sulfuric acid so strong an acid in the first place. So generally speaking, an acid is any molecule that has a hydrogen atom that it can easily give away as a hydrogen cation. And whether or not it can do this and how easily this can happen depends more or less on whether or not the electrons that were holding that hydrogen atom to the molecule in the first place have a comfy place to go once it leaves. Full disclosure, this might make a little more sense if you've like seen my atoms and molecules video, if you haven't seen it. So sulfuric acid looks like this. And those oxygens are really what makes this like the strongest acid. Sulfur is rather flexible when it comes to holding on to electrons. Oxygen, on the other hand, is not. Oxygen, when it's bonded to something in a molecule, it creates this kind of like vacuum effect where it's just pulling on all the electrons in the molecule through all the bonds in the molecule. Now, it's doing this to the sulfur and to the hydrogens, but the sulfur is in the middle, so it's kind of getting pulled on equally by, all four oxygens, so it's going to be fine. Those hydrogen atoms, though, they are not happy. They are not happy at all. And they would much rather be attached to something else where they can actually feel some electron density, because that's what all atomic nuclei crave, that ooey gooey electron density. That's why they make bonds. So because the bond between that hydrogen atom and those oxygens is so weak, that hydrogen atom is just looking for anything it can attach itself to. Anything at all that's going to give it a little bit more electron attention than it's getting right now. It will pluck itself down onto this thing, what's called protonating it, and those electrons will just live happily on what's called the sulfate anion. But there's more here, because remember, there's 3 other oxygen atoms in this molecule. So there's this process where those electrons can kind of swap places with other electrons in the molecule, and this makes them even happier to let that proton just go. Now, sulfuric acid is so comfy at letting go of that extra hydrogen atom, what's called oftentimes the proton, that it will give this proton 2 things that you generally don't think of as being bases. Like, not like just baking soda or even like ammonia. I'm talking things like propylene. Propylene and other molecules that have this double bond situation can be protonated or have a proton added to it by other acids. But sulfuric acid is really good at doing this. And when it happens, you get this other kind of reactive species that's similar to a free radical, but not exactly the same. These are called carbocations. And the discovery of their existence and the very, very handy and important chemistry that they do in biological systems as well as just in the lab all kind of hinged on sulfuric acid in the first place. One of the places where these carbocations became very useful to us is actually in petrochemicals refining, where crude oil and fuel feedstocks have a lot of molecules in them that kind of look like propylene, that have like a double bond in it somewhere. And so in these alkylation units, sulfuric acid is used to generate carbocations from those little molecules, which then react with other small molecules in the fuel feedstock to generate larger carbon molecules in a process that increases the octane rating of gasoline. Pretty important, pretty important. Now, I know I just told you that like it's super acidic and all of that and very reactive. So you're like, whoa, but like working with it. Actually, one of the beautiful things about sulfuric acid, it's not that hard to work with. And that's a big part of why industry loves it. It's not very volatile. It doesn't evaporate into the air. It doesn't really catch fire or anything like that. It's not even necessarily toxic. It's just really, really corrosive. So like as long as you don't spill it and as long as you keep it cold, you ain't got to really worry about it that much. And you don't always need it super concentrated. But we definitely needed it. We absolutely needed it and wanted it. And by the start of the 1900s, we were like, yo, we need like another way to make it because this lead chamber process is not really going to fly. And that's how we figured out the way that we make it now, which is called the contact process. And it's kind of cool. I ain't even going front. The trick in that process is making sure that the sulfur dioxide turns into sulfur trioxide. The way they do that is by burning sulfur and then passing those gases through essentially a catalytic converter like the one on a car. Except this one has vanadium oxide in it instead of palladium, but it does the same thing. It takes the sulfur dioxide and just stitches an extra oxygen atom on it and it's sulfur trioxide. But the contact process has another cool nifty trick to it. It doesn't mix the sulfur trioxide in with water. No. It mixes it in with more sulfuric acid. And this makes this stuff called oleum, also known as fuming sulfuric acid. Think supervillain acid. Now, oleum wasn't necessarily new. Oleum had been known about previously. However, this was the first large industrial scale process for making specifically oleum. Probably, though, the most important use of oleum that was opened up by having access to it on a broader scale was in the synthesis of our first class of antibiotics. Before we had penicillin, the sulfa drugs, a few of which I think still get used today. You see, there is a very specific reaction that sulfuric acid can go through called a sulfonation reaction, which really is just kind of what it says, where you attach a sulfate group or the sulfuric acid bit to something else. In the case of these sulfa drugs, there are 2 key steps that have to happen. First, you have to take this molecule called aniline, and you have to perform a sulfonation on it. Then you have to attach ammonia to the other end of that sulfuric acid bit that you attached. But the key here is that In order to do this reaction on a meaningfully large scale and allow us to actually have access to these antibiotics in such a way that more people could use them, you needed oleum. But to make them to begin with, you need sulfuric acid. But yeah, as we got better at just like doing chemistry, sulfuric acid just kind of got better at holding us down. Experiments with sulfuric acid helped us know and understand like what you could do with molecules and make them happen. It literally helped give birth to my profession, to my like passion in life, synthetic organic chemistry. This video easily could have been like 2-3 times the length with the details that I decided to just leave out. Sulfuric acid, super important, full stop. It has allowed us access to so many important things cheaply and consistently throughout history, as well as just knowledge that is indispensable to us as a species. So thank you to the alchemists of old who cooked some rocks for funsies, and thank you to the chemists who kept tweezing out what you could do with this angry oil, and thank you to you for watching to the end. And maybe you too now have a little bit of love in your heart for sulfuric acid. As always, you got follow-up questions, definitely leave them in the comments. If you like this one, definitely appreciate if you hit that like button. If you really enjoyed my content and you want to see more of it, definitely appreciate it if you consider supporting me financially on Patreon or Ko-fi. And until next time, it's Dr. Kim Thug.